Okay, great. So our next talk is by Scott Rodilitz on online algorithms for matching platforms with multi-channel traffic.
Great. Thanks, Vahideh. We're going to try this and we'll see how it goes. Sounds great. So thanks everybody for being here early on a Saturday. I appreciate it. Thanks to the organizers. This has been a great conference so far. Excited to hear more work. I'm really excited to be a part of it. I'm going to be presenting on some joint work with three amazing co-authors, Vahideh Manshadi, Daniela Saban, and Akshaya Suresh. I should say my name's Scott Rodilitz. I'm assistant professor at UCLA's Anderson School of Management. Okay, so if you were fortunate enough to attend Karen Smilowitz's keynote talk yesterday, she mentioned a number of things, including volunteer clearinghouses. And I'm really happy that she did, because today I'm going to be talking to you about the biggest volunteer clearinghouse in the US. So this is an organization called Volunteer Match. And if you're not familiar with how these volunteer clearinghouses work, I'll give you a brief description. So they have, on the one side of the marketplace that they've set up, a bunch of different volunteering opportunities. And these come from a variety of different nonprofit organizations. They serve a variety of really important social causes. And then on the other side of the market, they have a bunch of visitors to their platform. So Volunteer Match in particular has more than 1 million monthly visitors to their platform who are looking for ways to volunteer their time. Okay, so when a visitor arrives on Volunteer Match's platform, most of the time they're going to use the recommendation algorithm that Volunteer Match has on their site. So they'll search for volunteering opportunities. They'll see a list of these opportunities. Maybe they'll find one that they like. They'll click. They'll see some details about an opportunity. And if they like that opportunity after reading a bit more about it, they can click this I want to help button. And that connects them to this organization. And then they can figure out how to best volunteer their time. So for these visitors, Volunteer Match is serving two really important purposes. Right? They're working as a search engine, and they're also working to facilitate this connection between volunteers and nonprofit organizations. Okay, so this again is a majority of traffic on Volunteer Match, but it's not the whole story. So this is what we're going to call internal traffic. Internal being, it uses the internal recommendation algorithm on Volunteer Match, and it represents about 70% of visitors to their platform. Now, the other sizable minority of visitors are what we call external traffic. So this external traffic are visitors that bypass the platform's recommendation system and simply arrive directly to an opportunity page. Now, this can happen for a variety of reasons. The most common is some advertisement on the platform or on some other social media platform. So something like a LinkedIn advertisement or a Facebook post about a particular opportunity. Someone sees that, clicks, and arrives on Volunteer Match's site. So these people use Volunteer Match simply to facilitate their connections, not as a search engine. Okay, so we want to think about how this impacts what Volunteer Match should provide in terms of their recommendations to arriving visitors. Okay, one thing to keep in mind before we get into what Volunteer Match should do is that all of these opportunities have some finite capacity for volunteers. So this example that I've showed on the right needs 50 volunteers. Okay, so let's get into some of the data on VM's platform. So we can look at a sample of 100 different opportunities. I'm going to keep these opportunities somewhat homogeneous. So I'm going to look at virtual opportunities, and I'm going to look at only opportunities with a capacity of 10. And despite these similarities, you'll see there's big discrepancies in how many signups these opportunities get. So right on the left, you'll see there's a handful of opportunities that don't get any. Obviously, it's bad for those opportunities. I want to also emphasize that on the right for you guys, the number of opportunities that are getting a lot of signups, that's also bad for them for a couple of reasons. First, it stresses the volunteer management resources of those organizations. And second, if you're a volunteer and you sign up for one of these organizations that have a lot of other signups, now either they won't contact you back, and that can be discouraging, or you'll show up and there's not much for you to do, and that's also fairly discouraging. So right, this is an unfortunate outcome for many different participants on this platform. So why is this happening? Well, there's a couple of reasons. As you can see, some of these excessive signups come from external traffic, but some of them also seem to be coming from the platform's recommendation engine itself. So what we want to think about in today's talk is how we can design recommendations on the VM platform, taking into account this multi-channel traffic with the goal of maximizing useful signups. So for today's talk, I'm not going to try to make any value judgments about whether volunteering for one organization is better than volunteering for another. I'm just going to try to say, how can we get the most volunteers up to the capacity of an organization across all organizations? Okay, great. So before getting into our model and algorithm for dealing with this, I want to briefly mention that this type of phenomenon arises in a variety of contexts, not just on Volunteer Match. There's other platforms in the nonprofit sector where we see something like this. There's other platforms in the private sector where you see, again, a platform with a search engine that's used sometimes for its search engine and sometimes not. Happy to go into details about that if you have questions offline, but just want to briefly mention that this is a broader phenomenon. Okay, so let me give you a very high-level overview of our model. I'm going to keep things extremely simple today, so you're going to feel like there's some very simplifying assumptions. That's for the purpose of explaining things. I'm happy to talk about how we generalize what we do to more practical settings, and I'll touch on that briefly at the end. But we're going to think of this problem of deciding what to recommend as an online matching problem. So in that literature, you normally have a set of offline agents and a set of online agents. So in our context, the offline agents are going to be the opportunities. These are going to be known in advance, and they're going to have some known capacity. The online agents are going to be our volunteers. They're going to arrive sequentially, one in each time period. And when they arrive, they're of one of two types. They're either going to be external or internal traffic. So if they're external traffic, they're going to be compatible with a single opportunity, and they're going to directly sign up for that opportunity. If they're internal traffic, the platform's going to see which opportunities they're compatible with, and then we'll choose one such opportunity to recommend, and then we're going to assume that this volunteer will just deterministically sign up for that opportunity. Our goal in all of this is to maximize the total amount of capacity that gets filled. And the main challenge that we face is that we don't know the arrival sequence of volunteers in advance. We don't know who's going to show up in the future, whether they're internal or external traffic. If they're internal traffic, what they're going to be compatible with, anything like that. Okay, so we want to design an algorithm that does a good job. How are we going to define whether an algorithm has done a good job? Well, we're going to leverage something from the computer science literature called the competitive ratio. Many of you might be familiar with. Essentially, what we're doing is comparing the performance of an algorithm to a different algorithm that knows the full arrival sequence of volunteers in advance. Okay, so we're going to leverage some results in the literature which show that, okay, if there's no external traffic and if all capacities are large, we can achieve a competitive ratio of 1 - 1 over E. This comes from the online advertising literature. It's a nice paper by Mehta, Saberi, Vazirani, and Vazirani. And I'm going to refer to their algorithm a couple times in this talk as MSVV. Okay, the other thing to keep in mind, though, in this context, right, where we do have external traffic, if everything's external, there's no decisions to be made. So we're going to do just as well as someone that knows the arrival sequence in advance. So the way we're going to think about this problem is by parameterizing the competitive ratio by this parameter beta, which is going to represent the amount of external traffic in the system. So larger beta means more external traffic. And we want an algorithm that performs well regardless of that amount of external traffic. All right, so how are we going to do that? I'll give you the very quick summary of our algorithm. I think that's, it's a conference on, among other things, algorithms, so it's good to see exactly what we're doing. And it's pretty straightforward. So we have two counters for each opportunity, one for how many signups come from external traffic, one from how many signups come from internal traffic. And the only decision the algorithm needs to make is which opportunity to recommend to this internal traffic. And it's going to do that based on this function. This is a somewhat complicated function. The only thing I want you to notice is that it's decreasing in both the number of internal signups and the number of external signups. Now, where does this come from? Well, it's motivated by that algorithm that I mentioned previously, MSVV. It's quite similar. The key difference is that we're distinguishing based on the channel of traffic that the signup comes from. And this is going to enable us to make stronger guarantees. Okay, one other thing I want to mention about this algorithm is that nowhere in its description does the parameter beta appear. So we have this algorithm, and it doesn't need to know how much external traffic there is. So this is a nice feature. Many platforms like Volunteer Match don't know the extent to which they're going to have external traffic over some time period. Okay, so I'll briefly summarize the theoretical results we get from this algorithm, which we call adaptive capacity. So first, we want to say, what's the best that we can hope to do? That's given by this blue curve, the solid blue line. Basically, no algorithm is going to do better than this solid blue curve. And this is due to the limitations of making decisions when you don't know the arrival sequence of volunteers, when you don't know who's going to show up. Now, we're able to achieve almost exactly that level of performance using our adaptive capacity algorithm. That's shown by this dotted blue line. And I want to emphasize that it's really close to the solid blue line for every value of beta. So, right, it's near optimal for any amount of external traffic without knowing how much external traffic there is in advance. And I also want to point out that compared to kind of the state-of-the-art online advertising algorithms, we do see significant differences in the guarantees once the amount of external traffic gets large. So there is a gap between this lower bound on adaptive capacity given by the dotted blue line and the upper bound on MSVV given by that dotted red line. Okay, like I said, near optimal without knowing the amount of external traffic in advance. A few references about the proof technique. It's a kind of a fun proof. Happy to talk about it more offline, or you can check out the paper for those details. I want to mention, again, we do consider much more practical settings in the paper. So we look at what happens when, instead of having a deterministic recommendation, right, you make a recommendation and the volunteer signs up. What if you make a recommendation and they may or may not sign up? We also look at what happens when you make a set of recommendations, either in a ranked list or some assortment, and we get similar theoretical results with some differences based on the context. Okay, so that's it for the theory portion of this talk. I want to talk a little bit about some simulated results based on this algorithm, and then at the end I'll talk about kind of ongoing implementation efforts at VM. So to see how this algorithm might do in practice, we first took our algorithm and tried to simulate it. We tried to be as faithful as we could to the VM setting. So we took a sample of opportunities. We estimated conversion probabilities based on historical data. We took the arrival sequence directly, essentially from the platform. It's hard to predict what volunteer choice is going to look like. We didn't quite have the data to do that. So we borrowed a very common model in the literature called the cascade model. And so using this, and because we're limiting our set of opportunities to only 100, we're able to compute how our algorithm does, how a proxy for current practice does, and how this opt would do. Now, it's impossible to exactly calculate this opt, but we can calculate a linear program upper bound on it. And so what we see are a couple of key things. First, our algorithm, along with kind of the state-of-the-art online advertising algorithm, MSVV, does significantly better than current practice on Volunteer Match. And both of these more sophisticated algorithms do much better than their theoretical guarantees on this more practical instance. And this is, again, compared to an upper bound on something that knows the arrival sequence in advance. So we're encouraged by these results. I'll summarize now kind of what we've done and what we're going to do next. So in this talk, I hope I've convinced you that we have a new model for an important phenomenon on a variety of platforms, not just Volunteer Match, that we call multi-channel traffic. We've created a new algorithm, which is near optimal for any amount of external traffic, even without knowing that amount in advance. And so going forward, bolstered by both the strong theory and the promising simulation results, we've implemented an algorithm inspired by this work on Volunteer Match's website. And we're currently running some experiments with that algorithm to kind of quantify the gains in performance that we can expect to see. So Akshaya Suresh, who's a fourth-year PhD student who's a co-author on this paper, she's taking the lead on some of that empirical work. So if you have questions about that, I'm happy to answer them, but I'm also happy to direct them to her. So I'll pause there. Thank you so much for your attention. And I think I have some time for questions. Great. So if there's a question or two. Happy to take them.
Hi, thank you for the interesting talk. I was wondering if you could explain a little bit about what your algorithm is doing differently for the internal and external volunteers and like why there's, I mean, obviously you're taking advantage of the fact that they behave differently, but yeah, I was wondering if you could explain a little bit more about that.
Yeah. Happy to give some intuition. So I went over this quickly for sure. So basically the idea is if you knew all the external traffic in advance, what would you do? So you would reduce your capacities by that amount, right? You just have some deterministic filling of this capacity. And so if you knew it, you would reduce your capacities by that amount. So that's what we're essentially doing in our algorithm. And that's a little bit different than what's been done before. You can think of external traffic as like degree 1 arrivals, if you think about like the abstract matching problem. And so we're treating our degree 1 arrivals differently than our degree 2 or more arrivals. And that gives us better performance when we're comparing ourselves against something that will make the same decision as us for those degree 1 arrivals, but might make a different decision than us for the degree 2 plus arrivals.
Okay, got it. Thank you. And I was also wondering, do you think you could do like improved performance if you did know beta? Or is that like a gap that's
Good.
you
So that's a
can't
really good
extract?
question. So in the very simple setting that I described to you, I feel very strongly that this gap is like a gap in our proof. It's like very hard to get things exactly right. But I think there's no actual gap like in performance. Now, when you think about a more general setting, like some of the extensions that I considered, here's where I think there may be some value in knowing beta. So our results degrade a little bit depending on how general assumptions you make. And there, I think knowing beta might enable you to show something a little bit stronger.
Okay, thank you.
Great question.
Hi. Also, thank you for the talk. I was just curious again, also with your algorithm, is it as, I don't know if you were presenting it in a simpler form for the talk, is it as simple as this, that you're not using like a randomized ranking or something like that? And for the extended case, are there major changes to the algorithm or is it more or less this idea?
Good. Great question. So in the extended version, and the reason I've presented it like this, even though this is kind of an overcomplicated way of presenting it for this simple model, so things get a little more complicated when you have stochastic sign-up probabilities, so like basically different popularity of different opportunities. So given that I've shown it like this, all you need to do for that setting is add a multiple by the weight. So if you have something that has a probability of sign-up of 50%, you just multiply this by 0.5, compare it to something else that has a sign-up probability of 10%, you multiply that by 0.1. And this would then extend very simply to that setting. I think that answers your question, but I think I'm missing one part. Oh, good. Yes. So for this simple setting, yeah, we're not doing anything more complex than this. It's essentially in each step, you're making a greedy decision based on this metric. Yeah, good question.
Hi, thank you so much. I was wondering, because you're thinking about each time step as a volunteer arriving, if you have in mind as well what time the event is actually happening and how far you are from that, and whether that finite horizon impacts the approach.
Good. So that's a great question. Again, this is one of those things that you can tailor our model in such a way to capture. So one way of doing that is by saying, okay, any internal traffic volunteer that arrives after a certain time is going to be incompatible with an opportunity that expires or that runs out of time. So you can kind of build that into the compatibility. Now, one thing that doesn't capture is the fact that, okay, if you have that information, maybe your upper bound also goes up. And how do we do compared to that upper bound? So we'll be able to do even better if we had that information. But when we're comparing ourselves against some optimal algorithm, maybe that gap might get bigger. Maybe it can use that information better than us. And I don't have anything to say about that.
Let's thank Scott again.